Hey everyone, welcome to my stats final presentation. I chose to do my presentation on college data, particularly the age and credits of college students. First, we'll move to the summary sheet. We have our frequency table here and our frequency histogram, which is the most important thing. Our mean is 13.2, our median is 13.5, and our mode is 12. So the frequency histogram is right skewed, so it's not bell-shaped, and it is unimodal here from 11.5 to 14.5. So because our data is skewed, the median is going to be the most relevant measure of center on page 70. We know that. It is not affected by outliers as the mean would, and the mode is just not a good measure of center for our data. In our presentation, identify this measurement closest to the mean. So when we have standardized data, when the standardized data is close to 0, it means that that point is getting closer and closer to the actual mean. And if you have 0 as a standardized score, that means it's actually the mean. So 13 is going to be that because it is the closest score, standardized score to 0. Lastly, the percentage of data beyond 2 standard deviations from our mean. So 2 standard deviations would be about 6. So 13 plus and minus 6.14, which would be 6.86 and 19.14. And the only value below this is 3 right here. So that means that only 3.33% of our data is outside of 2 standard deviations from the mean. 1/30 is 3.33. But Shibev's rule says that 75% of data will fall within 2 standard deviations and 25% will fall outside. But however, my data set here has a lot less data fall outside of 2 standard deviations. So you can see that here. So that means that my data is more close to the mean, which we can obviously see right here. It's very centered, it's very clustered. So that my data is actually much closer to the mean than Chybovsky's rule says. Next, we have our confidence interval, and we are determining the percentage of the population that have earned at least 15 college credits. So in this sample, we have 12 that have above 15 because we have to do at least 15. So we have 15 and up. That is x over n, so 12 over 30 is 0.4. And then we can compute our confidence level. We were asked to use a 90%, our lower and upper bounds. So with this, we can tell that we can be 90% confident that the true value of the population proportion is between 39 and 9.90 and 40.1% of people, and our margin of error is very low. Next, we have our hypothesis test for the mean. So our question says to test the claim that the mean age for this population is more than 19 years. So our alternate hypothesis is going to be our claim. We are not dealing with more than, less than. We're just dealing with, more than or equal to, less than or equal to. We're dealing with more than. So our null hypothesis would be the converse of this, and it would be greater than or equal to 19. However, our test statistic falls very heavily below the critical value. We are using a right-tailed test because this is more than. Our test statistic falls very below our critical value, so we have to fail to reject this null hypothesis. But there's also not sufficient evidence to support at the 0.05 significant level that the population mean age is more than 19 years. We've actually found that the population mean age is 13.3. So there's not enough evidence to support this conclusion. Lastly, we have our correlation test. So this is the initial data that I had gathered. Oop, there it is. And you can see this point out here at about 3014 and this point at 24.3. They're both way outside the range of data. So the point at 30 is very far out and the point at 24 is very below. So it's going to affect the accuracy of our graph. So I ended up removing those 2 points as my outliers, and this is my updated graph. You can see that those 2 are removed. So we were able to determine with these values that there is not a significant linear correlation between age and credits earned. So we can tell by our correlation coefficient, the closer it is to -1 and 1, the stronger the correlation will be. But however, because our correlation coefficient is closer to 0 than it is to 1, it's not strong at all. It's actually negative, and as the correlation gets closer to 0, the significance of the linear correlation decreases. So because of this, this means that the regression line is not a reliable predictor of the values due to this weakness. And we can actually see this come into play here. We know that as college kids get older, they tend to take more classes, not fewer. So this doesn't really make sense, estimating the age of a person if they have earned 18 credits hours. So we can use our Desmos graph and we plug in y equals 18 and we get that person would be 12 years old, which doesn't really make sense. I don't know any 12-year-olds that are taking 18 credit hours a semester. And then question 5, we plug in the x value. So we would plug in for x and we would get 10.004. So which of these estimations is more trustworthy than the other? Well, obviously, the 12-year-old doesn't make sense. However, it is the more trustworthy one because it is in the range of our y values. Our age is our dependent variable, and then our credits is our independent variable. So that's why they're placed on the x and y axis, but we have data for 18 credits here. We don't for when the person is 25, so we would be extrapolating that data. We're making a guess, and that's not trustworthy because we have actual data here to back this up, even though it's pictured on the age range on the scale, it's still more trustworthy. And we can also see that when I did remove those other points, the p-value gets a lot smaller. So that means that the linear regression line is going to be more reliable. However, you have to take into context which question you're asking and make sure you're not extrapolating your data. And so that is my final presentation. I hope you all had fun this semester and enjoyed this presentation. Bye-bye.